Hi, good day again to everyone. So, we are now entering Unit 2 of Module 1. So, in Unit 1, we have seen how to expand a binomial and how to find the rth term of the binomial. So, in Unit 2, we will now be having factoring of a polynomial. And just a quick review, when we say we have a polynomial, it means that we have several algebraic terms that are being added together. And when we say algebraic terms, we have expressions, let's say, that would now look something like this. So a polynomial will be involved with variables, or we have literal coefficients. It can also be involved with numerical coefficients, and we can also see some exponents. So if you like that, we can put an exponent here. So we have exponents also involved for polynomials. And in Unit 2, our goal is to factor our polynomials. And when we say factor a polynomial from a sum, we would like to produce a product. So when we say factors, isn't it that we have seen the term in the operation on multiplication? Every term in a product is what we call a factor. Therefore, if we want to factor a polynomial from a sum or sum and difference, sum or difference, we would now like to create a product. And each element in our product is what we call our factors, or a factor. This is a factor, this is another factor. And of course, whenever we are factoring a polynomial, we want each factor to be in its simplest form. So when we say in its simplest form, it can no longer be factored in any format. And in Unit 2, we have a few learning outcomes. So the first one is to identify and factor the greatest common factor, or the GCF of a polynomial. 2, we have factor a difference of two squares. 3, factor a perfect square trinomial. 4, factor a trinomial using the trial and error method. And 5, factor by grouping. And of course, together with this, we must be able to identify what method of factoring must be applied in a given polynomial. So let's now start our factoring. The first type of factoring that we will have is what we call our common monomial factor. So from the title itself, from our polynomial, we will now find a common monomial. So when we say monomial, single term, that can be factored out from the entire group. So basically, the common monomial factor will be given by something like this. So let's say we have the polynomial AB plus AC, and in here we can find that A is a common monomial factor. Therefore, what we will do is the common monomial factor will now be factored out. So we factor out the common monomial factor, then that will now be multiplied by B plus C. How did we get B plus C? AB was divided by the element that was factored out, giving us B. Then AC divided by A will be equal to C. So that will be the process. Observe your polynomial, find a common monomial factor, factor out that monomial, then multiply it by. So what will be the terms left here? Just divide each term in the polynomial by whatever term that you have factored out. Let's look at this example. So example number 1, we have 8x to the fourth minus 4x cubed plus 10x. So if we are given an expression something like this, what we can do is inspect. So inspect. So what do we do? Maybe we can first consider our numerical coefficients. And looking at our numerical coefficients, we have 8, 4, and 10. Isn't it that the three numerical coefficients given, all of those terms can be divided by 2. So meaning 2 is a common monomial factor. And then we go to the literal parts or to the literal coefficients. And looking at the literal coefficients, we have the variable x in each expression or in each term of the polynomial. Now, if we find a literal coefficient to be common, the clue there is we always factor out the one with the lowest exponent. So in this case, we factor out x raised to 1. So we factor out x raised to 1. Thus, the common monomial factor is 2x. And then, what will be the terms inside the parentheses? We now divide each term of the polynomial by whatever term that we have factored out. So you have 8x to the fourth will be divided by 2x. 8 divided by 2, 8 divided by 2 will be 4. And then x to the fourth divided by x will be x cubed. So this will be x cubed. And then minus, we have 4x cubed. We divide it by 2x. 4 divided by 2 is 2. X cubed divided by x will be x squared. Okay. So that will be minus 2x squared. So minus 2x squared. And then plus 10 divided by 2 will be 5. And then x divided by x will be 1. So that will now be our final answer. We have 2x times 4x to the fifth. Let me just fix that. That will be, no, that's 4, what was that? That should be x cubed. 4x cubed, we just fix that. 4x cubed minus 2x squared plus 5x. If you want, plus 5 I mean. If you want to check if your final answer is correct, then you can just go back to your distributive property of multiplication over addition. So you just distribute 2x to each element here. It should give you the original expression. Okay. Let's have a second example. Second example, let's say we have this expression or this polynomial. We have 9ab squared minus 6ab minus 3a minus 3a. Again, the technique is inspect your numerical coefficients. We have 9, 6, and 3. So obviously, we can divide the numerical coefficients by 3. Then for the literal coefficients, all the terms are involved with our literal coefficient a. And the lowest exponent is 1. The first two terms, we have b. But for the last term, we don't have b. Therefore, b is not a common factor. So we will just factor out 3a. So dividing this by 3a, 9 divided by 3 will be 3. A divided by a will be 1. Then we have b squared. Minus 6 divided by 3 will be 2. A divided by a will be 1. We're left with b. Minus 3 divided by 3 is 1. A divided by a is 1. So that will now be the final result. Another example. Let's say we have 20 a cubed b plus 8 a b to the fourth, let's say, minus 12 a squared b squared. So let's observe. For our numerical coefficients, we have 20, 8, and 12. For our numerical coefficients, we can factor out 4. 20 can be divided by 4, 8 can be divided by 4, 12 can be divided by 4. And then we find a as a common element or as a common factor. The lowest exponent is this, 1. So we have a is a common factor. Each term in the polynomial, we can also find b, where b is a common factor. B raised to 1. 1 is the lowest exponent, so we factor out 4ab. So factoring out 4ab, 20 divided by 4 is 5. A cubed divided by a will be a squared. B divided by b is 1 plus 8 divided by 4 is 2. A divided by a is 1. B to the fourth divided by b is b cubed minus 12 divided by 4 is 3. A squared divided by a is a. B squared divided by b is b. So we now have our final result for AB times 5a squared plus 2b cubed minus 3a. So that's the process for the common monomial factor. So we just inspect a common monomial from the given terms in the polynomial. We factor that out, and then the remaining term in the parentheses will be obtained by dividing each element in the polynomial by whatever we have factored out. The second type that we will be considering is what we call the difference of two squares. So look at the title. We have the difference of two squares. So what do we mean when we have difference of two squares? So first, the operation is subtraction between two terms that are perfect squares. So when we say a term is a perfect square, it means we can extract its square root. Or in other words, we can find an element multiplied to itself that will give us the original term. Okay, so that's the perfect square. So we have the difference of two perfect squares. And this part will now give us the factored form of the difference of two squares. So we have the first term squared minus the second term squared. This is just equal to the first term plus the second term multiplied by the first term minus the second term. So we just get the first term, okay, plus the second term multiplied by the first term minus the second term. So if we have this, a squared minus b squared, we have a difference of two squares. Therefore, if we now get the factored form of this, we copy the first term plus the second term multiplied by the first term minus the second term. So that's for the uh, process of the difference of two squares. So let's have some examples. Example number 1. Let's say we have the expression b to the fourth minus 25. So if we will look at this expression, b to the fourth minus 25, isn't it that b to the fourth can be expressed as b squared, squared, that's b to the fourth. 25 can be expressed as 5. 25 can be expressed as, oh wait, let me erase that again. What's happening there? Okay, And 25 can be expressed as 5 squared. Therefore, if you will inspect this, b squared is the first term and 5 is the second term. Both are perfect squares and the sign between them is subtraction. Therefore, it is a difference of two squares. And if it is a difference of two squares, according to the rule, this will have two factors involved. We just get the first term plus the second term multiplied by the first term minus the second term. So there you have it. That's the difference of two squares. Again, if you want to check if your answer is correct, just proceed with the distributive law of multiplication over addition. So you just distribute. So you have b to the fourth minus 5b squared plus 5b squared will be 0, and then that's minus 25, which gives us the original expression. Another example, second example. Let's say we have the expression 4x squared minus 49, let's say y squared. So if you would like to express this as first term squared minus second term squared, then if you will look at 4x squared, that's the same as 2x, the quantity squared. So you need here your index laws. So 4x squared is just the same as 2x, the quantity squared. That's 2 squared is 4, x squared is x squared. Minus, similarly, for 49y squared, square root of 49 is 7. And then we have square root of y squared is y. Then this is quantity squared. So if you will inspect this, we have a difference of two squares. And according to the rule, if we will now factor a difference of two squares, we get two factors. We copy the first term plus we copy the second term. First term plus the second term multiplied by the first term minus the second term. Okay? And a third example. For the difference of two squares. And let's say we have 16 y to the fourth minus, let's say, 81 x to the, let's say, x to the 8th. So this will now be the same as 4y squared, the quantity squared. That will be 4, 16y to the fourth minus, that will be 9x to the fourth raised to 2. For 81, 9 squared is 81, x to the fourth squared is x to the 8th. So you will find here that our expression is again a difference of two squares. Since we now have obtained a difference of two squares, according to the rule, we will have two groups. We just copy the first term plus we copy the second term, 9x to the fourth. And then the second group, we have the first term minus the second term, which is 9x to the fourth. But if you will observe this very closely, for the second factor, we have again a difference of two squares, isn't it? It's a difference of two squares again. Why? Let's show it. If we will rewrite the second expression that will now be, so let me just copy the first one. We have 4y squared plus 9x to the fourth. 4y squared is the same as 2y, the quantity squared, minus 9x to the fourth is the same as 3x squared, the quantity squared. So the second expression is again classified as a difference of two squares. Therefore, if it's a difference of two squares, then, so we just copy the first factor, that's 4y squared plus 9x to the fourth. We do not have a rule that is called a sum of two squares. We only have as the difference of two squares. So we create again two groups for this. As the rule states, copy the first term plus the second term multiplied by the first term minus the second term. And there you have it. We now have the factored form of 16y to the fourth minus 8x to the eighth. So this is what I was mentioning earlier, that each time we factor a polynomial, it must always be in the simplest form. Each factor must not be factorable anymore. So we have 2 already, the difference of two squares, and common monomial factor. So let's now proceed with the third. The third type is what we call the perfect square trinomial. And for a perfect square trinomial, so we have a trinomial, meaning we have three terms in our polynomial, and it's a perfect square. So when it's a trinomial, a perfect square. So let's have an illustration here. A trinomial will be a perfect square if we have two perfect squares. So in this case, we have a squared, b squared are perfect squares. And then the remaining term is twice or two times the product of the square roots of the perfect squares. The square root of a squared is a, the square root of b squared is b. So there you have it. So if you have this as a perfect square trinomial, again, you have two perfect squares, and the remaining term is two times the square root of the two perfect squares. And the factored form of this, so let's proceed here. Let me just do the shortcut. We can remove this section. So if we will now look at the shortcut, the factored form of this is we get the square root of the first perfect square, and then we get the square root of the second perfect square, and then whatever sign we have here, that's also the sign that we put here. Everything raised to 2. And looking at this illustration below, this is still a perfect square trinomial. We have two perfect squares, right? We have two perfect squares, and then the remaining term is 2 times the product of the square root of the perfect squares. And to factor this, we get the square root of the first perfect square, and then we get the square root of the second perfect square, and then whatever sign we have here, that's also the sign that we include here. Then everything raised to 2. So before you can factor a perfect square trinomial, you have to check first if the trinomial given is indeed a perfect square trinomial. Let's look at an example. Let's have this example here. We have x squared plus 8x plus 16. So clearly, x squared is a perfect square, obvious. 8x is not because x has an exponent 1. So definitely this is not a perfect square. 16 is a perfect square. So actually, we can rewrite that as x squared plus 8x plus 16 is the same as 4 raised to 2. So let's verify if we have a perfect square trinomial. We have two perfect squares. We have x squared and then 4 squared. So we have two perfect squares. So we have to check if the remaining term is 2 times the product of the square roots. So we have 2 times the square root of x squared is x. The square root of 4 squared is 4. So this is 8x. So we find here 8x. So indeed, this is a perfect square trinomial. We have all the conditions satisfied. Therefore, if we will now factor this according to the rule, so we can use this. We copy. So if you already have the format of the perfect square in this manner, the easiest way to factor this is copy the base. So that's x. And then copy the sign. And then copy the base. Everything raised to 2. So copy the base. Copy the sign. Copy the base. Everything raised to. First, you must always check if it's really a perfect square trinomial. Copy the base. Copy the sign. Copy the base. Everything raised to. Okay. Second example. Second example. Is this a perfect square trinomial? So let's inspect. 25y squared is a perfect square. We can write it as 5y, the quantity raised to 2. 10 is not a perfect square. So we just copy that, minus 10y. 1 is a perfect square because 1 is equivalent to 1 squared. So initially, if we will check this, we have 2 perfect squares. We have 2 perfect squares. And what do we need to do now? We get the square roots of the perfect squares, and then we multiply this by 2. What do we get? This is 10y, which is equal to this. Therefore, this is a perfect square trinomial. And if it's a perfect square trinomial, according to the shortcut that I have mentioned, we just copy the base, that's 5y, copy the sign, minus, copy the base, everything raised to 2. Okay, so you can verify if the answer is correct by expanding that again. We have the third example here. So for the third example, is this a perfect square trinomial? Let's check if it's a perfect square trinomial. X to the fourth is a perfect square. That's the same as x squared raised to 2. 25y to the fourth is a perfect square. So let me write it here. That's 5y squared raised to 2. Remember, addition, subtraction, both can be commutative. Addition is commutative, subtraction is commutative. So we can interchange the places. So that's minus 10 x squared y squared. So initially, we have seen that the condition for 2 perfect squares was satisfied. Now, what do we need to check? So if we have 2 perfect squares, we get the square roots of those. We have x squared, and then we multiply it by 5y squared, and then we multiply this by 2. And we get here 2 times 5 is 10, x squared, y squared. 10, x squared, y squared. So it is indeed a perfect square trinomial. So if it's a perfect square trinomial, we copy the base, that's x squared, we copy the sign, that's minus, we copy the base, 5y squared, and then everything raised to 2. And that will now be our final result. So in this video lecture, we have discussed three types of factoring: common monomial factor, the difference of two squares, and the perfect square trinomial. So in your module, you will find some other examples there. You can review those examples, and you can also find there some exercises. So please solve those problems as your practice problems. Okay? So in the next video, I will be discussing the remaining types of factoring, factoring by trial and error, and then factoring by grouping. Okay? So God bless you all till our next lecture.